Unmanned aerial vehicles are widely used for high-altitude orthomapping. This process involves capturing images at specific intervals with their corresponding coordinates and then aggregating them to create a high-resolution orthomosaic. The quality of the orthomosaic is heavily dependent on the input images. High brightness areas or low light conditions can significantly impact the final result. To address these limitations, we propose using event cameras. These bio-inspired sensors offer a higher dynamic range compared to traditional CMOS-based cameras, enabling them to capture detail in challenging light conditions. To record our data, we mounted an RGB camera, an event camera, a temperature-compensated IMU, a multi-constellation GNSS, and a single-point LiDAR into our custom-built Falcon 4 UAV. All data is collected by an onboard computer. Precise time synchronization is crucial when working with high-frequency sensors like event cameras. We achieve this with a dedicated synchronization board that generates signals to trigger or timestamp sensor measurements. A unique time pattern embedded at the beginning of the signal ensures accurate alignment during post-processing. We collected 15 different sequences at different times of the day, capturing different light conditions, flight speeds, and event camera biases. This data is publicly available, providing valuable benchmarks for future research. Our pre-processing pipeline adapts event camera data into a format compatible with existing orthomapping tools. We use E2bit to synthesize frames from events. We then filter for high rotation and spatially undersample the generated images. To combine the RGB and event data, we apply pan-sharpening techniques like mean, ESRI, and Brovie fusion. The resulting fused images are then fed into OpenDrawMap. We created a ground truth orthomosaic using the highest quality data from our dataset. We can then compare our test orthomosaics, aligning the reconstructions using manual feature matching and homographies, and evaluating the PSNR and SSIM metrics. We tested two challenging sequences with high dynamic range and low light conditions. In the high dynamic range sequence, on a sunny day at noon, our approach showed qualitative improvements compared to RGB. For instance, the texture of a sidewalk under direct sunlight is better reconstructed thanks to the event camera data. In the low light sequence, flying at dusk, our method significantly enhanced brightness and detail, particularly in shadowed regions. As a consequence, the PSNR and similarity metrics are better than RGB. Thank you for your attention.